So where we left off on last week's lecture was this last little section called oxidation reduction reactions. And what you're going to get here is the about 10 slide summary of oxidation reduction reactions. If you were taking this in a higher level chemistry course, oxidation reduction reactions would take an entire lecture and they would scar you for life. I still remember having to balance these things. Imagine balancing the problems that we balanced last week, plus adding electrons, plus charges, plus hydrogen ions, plus hydroxide ions, all in one massive equation. Remember that one where you keep going back and forth and back and forth? That is every problem for oxidation reduction reactions. You're not going to have to do that. Okay? You're just going to have a very basic idea of what an oxidation reduction reaction is. Oxidation reduction reaction is a reaction where electrons move from one compound or element to another. That is an oxidation reduction reaction. It's the movement of electrons. People call these redox reactions. Reduction, oxidation, redox reactions. Okay, that's what we're going to call them from here on, redox reactions. This is an example. In this case, we have zinc solid with copper ion in solution. And when you put those two together, what you get is zinc ions with copper solid. In this case, the electrons went from the zinc to the copper. Think about it. For copper to go from neutral to 2+, what had to happen to its electrons? It loses. When metals lose electrons, they become positive. And so to go the other way, copper went from an ion with 2+ to a metal with a 0 charge. It had to have gained electrons. Electrons don't come from nowhere. Electrons, in this case, came from the zinc. Zinc went from 0 charge to 2+. It lost 2 electrons. So the electrons went from the zinc to the copper. If you do this in the lab, what you get is, this is a piece of zinc sitting in a beaker full of a copper something solution, probably copper nitrate. The blue in the solution is the copper ions. Put the zinc in there, the electrons go from the zinc, from here, onto the ions in the water. But when that happens, you now have copper metal. The copper metal forms on the outside of the zinc metal. And if you look at the blue over here is not nearly as dark as over here, because the copper that is now this brown color was the blue. So the copper is coming out of solution. If you could take all this metal off, you would see that the piece of zinc metal is smaller. The zinc metal went from being a chunk, and it's now dissolved in the water. When we talk about redox reactions, we have some terms that we use. Okay? The first one is oxidation. Oxidation is losing electrons. Okay? And that one, I don't have an easy way to remember, but the way I remember it is it's the opposite of reduction. Reduction is gaining one or more electrons. Now think about things like chlorine. When chlorine forms an ion, what happens to its charge? Does it go positive or negative? Negative. If it goes negative, does that mean it gained or lost electrons? Gained. So if you gain electrons, your charge goes from 0 to negative, right? -1 is lower than 0. That charge went down on a number line. Does that make sense? Went from 0 to 1. That is reduced. That charge is getting reduced to a smaller number. That makes sense to me. That's how I remember reduce. If the charge is going down, that means it's gaining electrons. And so oxidation, by process of elimination, must be losing electrons. These happen at the same time. Because electrons don't magically get made, they don't magically get destroyed, and they don't magically go from over here to over there, and then over there, and then finally end up over here. They get transferred directly from one to the other. So oxidation reduction always happens together. And remember, the element whose charge goes down, whether that means going from, say, +1 to 0, +2 to +1, or 0 to -1, -1 to -2, think of it as a number line. If you go down on that number line, it is being reduced. If the charge goes up, it's being oxidized. So in this case, we look at the charges here. Okay? Chloride has a -1. Chloride always will have a -1. Copper, in this case, had a +2 because that 2 is there. Zinc is not an ion, so it doesn't have a charge. We write these numbers up top. We call these oxidation numbers, but to you, they are essentially charges. Technically, they're different, but in all the reactions that we're going to do, they're just going to be the same as the charges. So here zinc was 0, copper was +2, chlorine was -1. Zinc went from 0 on the left to +2 on the right. Did the charge go up or down? Up. It went from 0 to +2, which is up. And if it went up, that means it was oxidized or reduced? Oxidized. Oxidized. Copper went from 2 positive to 0. Oxidized or reduced? Reduced. It went down from +2 to 0. What about chlorine? What did it do? It didn't change. So it is not oxidized, it's not reduced, it just sat there. Okay. There are rules for assigning the oxidation numbers. And I cut all the complicated ones out because you don't even have to worry about them. Okay? All you have are the easy ones. Number 1 says the oxidation number of the atom in an uncombined element is 0. What that means is if you have just an element by itself, it's not in a compound, just like zinc was in that reaction. Zinc was just by itself to start with. The oxidation number is 0. Remember that, because you're going to forget. The sum of oxidation numbers on all the atoms in the compound or the substance equals 0. That's not earth-shattering news to you. Think of an ionic compound. The compound itself has no overall charge, right? NaCl has 1 positive, 1 negative, which is 0. Something like calcium chloride. The calcium has a 2 positive charge. Each chlorine or chloride has 1 negative, but because there are 2 of them, there are 2 negatives total. And so +2 and -2 cancel out. Oxidation numbers as a whole comes out 0. And the final rule is exactly what we learned in terms of charges. This says group 1 is +1. You already know that. It says group 2 is 2+. You already know that. And then group 17 is -1. You already knew that. And so take the charges that you would normally assign to these ions and just put them up top. And those are our oxidation numbers. So what is the oxidation number for magnesium as it's currently written? 0. It's not an ion, it's not in a compound. It's an element all by itself. so it's 0. What about the carbon and the chlorine? We didn't have a rule that told us the oxidation number for carbon. We have one for chlorine now. What was it? -1. So how can we figure out the oxidation number on carbon? Right. The second rule said as a whole has to add up to 0. So what is our total negative charge here? -4. And so this carbon, because there's only one of them, has to be 4 plus or +4. Does that make sense? Remember, they have to add up to 0. We have specific rules that directly tell us for some elements. If you don't have a specific rule for that element, you're going to have to use it by process of elimination because the whole thing has to add up to 0. If you had a compound that had 2 elements that didn't have a specific rule, you wouldn't be able to do that. Because you would know what the combined charge between the 2 is, but you don't know how to divvy that up. What about sodium chloride? What's the oxidation number on sodium? +1. And chlorine? -1. Okay. On the homework, you may get things like this, where you have to use a little bit of logic to figure out the other one. Okay? On a quiz or an exam, you're only going to have ionic compounds, where it's just look up here, put your charges in like you normally would. Okay? But you do have to remember that an element by itself is 0. And so the type of problem you'd see on a quiz or an exam is like that zinc and copper one we started the slides with. Nice catch. So where do we run across these redox reactions? Rusting is actually a redox reaction. So cars don't look like this anymore, but they used to rust all the time. Maybe not down here, but up north where there's all the salt, cars used to rust really badly. If you look at water sitting on a piece of iron, this is what's going on. You have the water, and you have iron here. You have the oxygen in the water. The electrons from the iron metal are going to get transferred into the oxygen with the water. And what happens when that occurs is your iron metal becomes iron ions. Iron ions dissolve in water. So when the rain falls off your car, your iron goes with it. Slowly over time, your metal goes away, and what is left is reacted with the oxygen. Same thing happens with other metals. Copper, think about a copper penny, a new penny versus an old penny. We talked about that, I think at the very beginning, the first lecture of the class, called that a chemical change. That's a redox reaction. Brass turns green. It reacts with the oxygen in the air. And silver jewelry will turn black. We can use what we know about redox reactions to prevent rust and corrosion from happening. You can just put paint on things. Rust-Oleum spray paint. Most of what it does is it just covers what you're spraying on. If it's not touching the water, if it's not touching the air, it can't react with the water in the air. In other cases, we use what we call sacrificial anodes. An anode is something that gives electrons. That's the negative terminal on a battery. That's where the electrons come from. And so, if you have a boat, if you ever look at the hull of a ship, there are these big chunks of metal on them. And If you have an outboard motor, there are sacrificial anodes on here. The most obvious one is just above the propeller. There's another little fin under here, and then there's some where it connects to the transom of the boat. That's zinc. Zinc is rust or corrodes easier than steel. So what happens if the water comes along and it steals an electron from the steel or the iron will then turn around and steal it from the zinc. And so overall, your steel or your iron didn't lose any electrons. And if it doesn't lose electrons, it doesn't corrode. So over time, instead of your iron corroding, your zinc corrodes. But these just pop off and you put a new one on. So they're called sacrificial. They corrode so that the good stuff doesn't corrode, and then you just replace it when it goes bad. They do the same thing on oil pipelines. If you get a rusting on your oil pipeline going through Alaska, that's not going to be good news. And they can't paint the whole thing. That'd be a lot of paint. They also don't want to have to walk up and down the whole thing every couple days looking for rust. And so they put these sacrificial anodes on it, and every once in a while they go through and replace them. Electroplating is essentially the reverse of a redox reaction. So yes, that is a gold-plated tellurium. Same thing goes for your gold-plated jewelry. Essentially what you do is whatever metal you want to put on something, you put it in solution. Say you want to put gold on a ring. You get something like gold chloride. You dissolve it in water, and then you put an electrical current through it. When you do that, it takes the gold, it reduces it from gold ion to gold 2+, to gold metal, and that gold metal has to go somewhere. So it sits on the outside of your ring and creates a coating. But it's very, very, very thin. Questions about redox? What you need, wow, what happened to that? I think there's a slide. It's an important slide. Oh, I blew past it. We're going to go back to this slide. So we talked about the definitions of oxidation and reduction, right? We also have terms that go with the reactants themselves. So oxidation and reduction are the processes of gaining or losing electrons. We said the element whose charge goes down is reduced. That element is the oxidizing agent. It seems backwards, but you have to remember that, okay? You're going to be asked this a number of times this semester. The thing that gets reduced is the oxidizing agent. And the thing whose charge goes up is oxidized. It is the reducing agent. So if we go back to our example, in this reaction, what element was reduced? Copper. It went from 2+ to 0. Is copper the oxidizing agent or the reducing agent? It's the oxidizing agent. What is the reducing agent? It is the zinc. Zinc was oxidized, which means it is the reducing agent. Okay? Questions like these, if they can ask you which element was reduced, which element was oxidized. They can ask you which is the reducing agent, which is the oxidizing agent. Your answer is always going to be something on the left side. Things on the right side don't have terms that go with them. The reducing agent and the oxidizing agent are always reactants. So if you have a multiple choice problem, you can immediately eliminate the things that are products. Now other questions.
What did you say the oxidizing agent was?
It's the thing that gets reduced.
Is what gets reduced, and oxidize is what gains?
If you're oxidized, you lose electrons,
Okay.
which means you are the reducing agent. If you gain electrons, your charge is going to go down. That means you were reduced. Your charge is reduced. And if you are reduced, you are the oxidizing agent.
If you are reduced, you are the oxidizing agent.
Correct.
And if you lose an electron, you are the
Oxidized, so you are the reducing agent.
So in this one, the zinc remained two. Zinc looks like it gained, right? Because
What's the charge on an electron?
2+.
What's the charge on an electron? What's the charge on an
Positive.
electron? Negative. Protons are positive.
You mean on zinc?
No, on electrons. What's the
Negative,
charge on one?
negative.
Negative 1. So, if the charge on the zinc went up, that means we lost negatives.
If it went up, we lost.
The reason charges happen is because you gain or lose electrons, right? You're gaining or losing negative charges, one at a time, with each electron.
Okay, because I see it's just zinc as solid, and when we go to the right, it's zinc 2+.
Right. And so which direction did the charge go?
Up.
Up. Which means it was oxidized or reduced?
Oxidized.
Oxidized. And so is zinc the oxidizing agent or the reducing agent?
Oxidizing.
No. It's backwards. The thing that gets oxidized is the reducing agent. The thing that gets reduced is the oxidizing agent. It's a matter of which direction you're looking at. Say I'm getting oxidized and you're getting reduced. That is describing what's happening to us.
Okay.
The agent term describes what we do to each other. Because I was oxidized, that means I must have reduced you.
Okay.
So I am therefore the reducing agent.
Okay, but then you gained something, right?
I said I was oxidized, which means I lost electrons.
Okay, I think I'm a little confused. Maybe it's going to take a little while.
Okay.
Yeah. I just wanted to understand that zinc is the oxidizing agent for copper.
No. Zinc is oxidized.
It's oxidizing.
So it is the reducing agent.
Oh, well, okay. When it has 2+, does it mean it lost an electron?
We lost 2. It went from 0 to 2+.
Okay.
That means it lost 2 negatives, and a negative is an electron. So it lost 2 electrons.
So it becomes oxidized?
Correct.
And copper becomes reduced?
Correct. The easiest way to remember it is to look at which direction the numbers went. That number on copper went down. It went from positive 2 to 0. That is down, right? That number got reduced. It is now smaller than it was. So copper was reduced, and by process of elimination, zinc was oxidized. We are going to move on to the next one. We started talking about stoichiometry. Stoichiometry is where your dimensional analysis is really going to come into play. I really, really, really strongly suggest using dimensional analysis for all of these problems. Okay? The units are going to help you. It's going to make it a very easy process to follow. It's essentially one conversion after another, and you'll see what we mean by that. So in the video, we talked about what the coefficients mean in a reaction. And we said it tells you how many of each thing react with the other reactants to give you how many of the products. So in this case, there's a 1 coefficient here, so 1 of these react with 5 of those to give us 3 of those and 4 of those. And it doesn't matter whether you're thinking about molecules or moles. You can go and use it for either way. So there are 4 types of stoichiometry problems. Getting harder, I don't even want to say harder and harder. They just get longer and longer. We have mole to mole conversions, grams to moles, mole to grams, and grams to grams. At the bottom of that slide, we have this essentially flow chart. Okay? In a stoichiometry problem, we go from one compound in our reaction to another. We can go from one reactant to another reactant. We can go from a reactant to a product. We can go from a product to a reactant, or a product to another product. It doesn't matter. You decide which compound you are starting with. That's going to be what the quantity that they give you in the question. And then you figure out which one you're going to. That's what they're asking for. The one you're starting with is going to be A. The one you're going to is going to be B. And so you figure out where on this flow chart you're starting. If you are given moles of A, you're going to start there. And you're going to work your way right until you get to where you need to go. If you are given moles of A and you just need moles of B, you just do one step. You got to go from here to here. That's 2 steps. You go from here to here, 3 steps, or here to here. We're going to do each one. Okay? In reality, none of them are more difficult than the other. But that middle conversion uses this mole ratio. And the mole ratio is just the coefficients. That is all it is. In this reaction, the mole ratio of oxygen to C3H8 is just 5 to 1. 5 to 1. That means 5 moles of oxygen is going to react with 1 mole of C3H8. So this is the first type of conversion, mole to mole conversion. So we're starting with 0.40 moles of C3H8. We're using dimensional analysis, so what unit has to be down here? Moles of C3H8. Where are we trying to get to as our answer? What in terms of a unit? Moles of oxygen. And so we want moles of oxygen. This is just a conversion factor, and the numbers come straight from the coefficients. So what is the coefficient on oxygen? It's 5. The C3H8 is 1. And you set it up so it's just 0.4 times 5 is 2. What is the mole ratio in this reaction of oxygen burning with benzene? So what's the mole ratio of oxygen to benzene? 15 to 2. It's that simple. 15 to 2. So just based off of that, without even doing math, can you tell me how many moles of oxygen are required to react with 1 mole of benzene? 7.5. So this says 2 moles of benzene requires 15 moles of oxygen. So if we have 1 mole at half, we need half that many, 7.5. But we can also do that with dimensional analysis. We can say 1 mole of C6H6, moles of C6H6 is just going to go down here. Now we want to get to moles of oxygen. What number goes here? 15. What number goes here? 2. Equals 7.5 moles of oxygen. This one you can't do in your head. How many moles of oxygen are required to react with 0.38? It's the same exact problem. We're just going to plug in 0.38 instead of 1. And that apparently comes out to be 2. Mole to mole conversion makes sense. This is the easiest one. It's right in the middle. All you have to do is take the coefficients. That's all it is. Just got to make sure you get the right one on the top and the bottom. If we were going to do this problem like this, 2.3 moles of oxygen to moles of CO2. What's the mole ratio you would use? 5 to 3. So if we write it out, we've got 2.3 moles of O2, moles of O2, moles of CO2. CO2 is 3, oxygen is 5. And you're done.
How do you get to say it's 5 to 3? I don't understand. How do you get that in the equation?
Coefficients. And so if I ask you the mole ratio,
Do we only get oxygen?
if the question is what is the mole ratio from oxygen to CO2, it is 5 to 3.
Okay.
Good.
From what you look at what you asked to what?
Right.
Okay.
So if the mole ratio from CO2 to oxygen would be 3 to 5.
From CO2 to oxygen will be 3 to 5.
Correct.
Oxygen to carbon dioxide would be
5
to 3. And that's what you use over
So
there?
here, your units will tell you. Because we started with moles of oxygen, oxygen has to be on the bottom here. So CO2 has to be on the top. And so that will put the numbers in the right place for you. You don't even have to think about which one am I trying, which one goes first. The units will tell you which one goes on the bottom, which one goes on the top.
Depending on what's produced? Is that how you do
What the
it?
question is asking, go from oxygen, go from 2.3 moles of oxygen to CO2.
Okay.
And so we're starting with oxygen, so oxygen has to be on the bottom here. And CO2 has to be on the top. So we do that, 2.3 times 3 divided by 5 is 1.4. How many moles of chlorine are needed? There's 1.4.
You're too quick to do this. Over here. Right over here. Thank you.
How many moles of chlorine are required to make 0.63 moles of aluminum chloride? This is the type of a reaction calculation you would do in lab if you know how much of a product you need to make. You say, I need to make 0.63 moles of aluminum chloride. And so you just say, how much reactants do I need then? I have as much reactant as I want, but how much do I need in order to give me the product that I want? So there's 0.62 moles aluminum chloride. What number goes here? 3, what number goes here? 2. 0.62 times 3 divided by 2 is 0.9. Now we're going to add another step. We're going to add a step to the beginning. We're going to go here from grams to moles. These problems are 2 steps. The second step is this step. It is exactly the same second step. It's just we're not given the moles of A. We're given grams of A. So we convert grams of A to moles of A, and then we do this. And you already know how to convert grams to moles. It's the same thing you were doing before. So you're going to take what you did before, do it in one step here, and then tack this on to the end of it. So this question says, if 80 grams of oxygen was produced, how many moles of KClO3 decomposed in order to make that much oxygen? So which of those 3 compounds up there are we starting with? What is A? Oxygen. We're going to start with oxygen in our calculation. And what are we trying to get to in the end? Moles of KClO3. So I'm going to start with 80.0 grams of oxygen. That's the only number I'm given. That's where I'm going to start. So what unit has to go down here? Grams of oxygen. When we get up here, we're essentially at this step. And so what unit is going to be here? Moles of oxygen. This first step is just converting our grams of oxygen to moles of oxygen. What number is going to go here? 1. 1 mole of oxygen weighs how much? 32. It's O2. It's diatomic. Each oxygen is 16. So that's 32. You got to add a step. What unit goes here? Moles of oxygen. And then what unit goes here? Moles of KClO3. It's this step. We're going to use our mole ratio. We're trying to get from moles of oxygen to moles of KClO3. What number goes here? 2. It's the coefficient on KClO3. What number goes here? 3. And that's it. We did one step, and then we did this step here. And then apparently I didn't put the answer on. Somebody have a calculator?
That's better than 9.
80 times 2 divided by 32 divided by 3. So,
grams. Oh.
oh, that
Yeah.
is the G. 1.6666. How many 6 we got? 3. 6, 7. 1.67 moles of KClO3. Question?
So you go by the 3 C3s and not the ones that you put in front of the
Right. These are not measured numbers, so the 6 figs are only the measured numbers. In this case, it's just the 1, just 3. Here's another one. 1.5 moles. So this is a moles to grams. So we're going to do the moles to moles, and then tack on moles to grams at the end. This one, we added a gram to moles at the beginning, This time we're going to do moles to moles and then moles to grams. The question says we're starting with 1.5 moles of KClO3. How many grams of oxygen will you make? So what number are you going to start with in the top left corner? 1.50 moles of KClO3. What unit goes here? Moles of KClO3. What unit do you want to put up here? Moles of oxygen. We're trying to get the oxygen, and so we want to get the oxygen, but we can't go from moles of KClO3 to grams of oxygen. So we have to go moles of KClO3 to moles of oxygen. What number goes here? 3. It's the coefficient. And here we have 2. Now we have to convert our moles to grams. What unit goes here? Moles of oxygen. What unit goes up there? Grams of oxygen. What number goes here? 1 mole weighs 32. 12.
72, sorry.
72.0.
Yeah.
Oh, why? 12.
7 kind of looks like a 1.
Sure.
72 grams of oxygen. So that's moles to grams. And then the biggest one is grams to grams. It's essentially that with a grams to moles at the beginning, or it's this with a moles to grams at the end. It's going to be 3 steps.
Is there going to be a different mass than grams, where we have to like change it to grams?
I can't think of anything that you would run into other than maybe kilograms. And I don't even know you're going to run into kilograms. I don't think you would say something 5 pounds, something like that. Yeah.
So which one is it that we're starting with for this one?
So this one, I'm actually, but I was, just as an example, here we went from moles to grams. To do it grams to grams, it's that type of a problem, but with an extra step here. This was grams to moles, to go grams to grams, so this type of a problem, plus 1 step down. Everybody got these? So what number in this problem is our starting point? 9.20 grams of sodium. And where are we trying to get to in the end? Grams of chlorine. So we've got 9.20 grams of sodium. It's my unit. Grams of sodium. It's my unit.
Why can't you go grams to grams? Why do you have to go through the moles step? Is it because?
How do you know how many grams of sodium gives how many grams of chlorine?
I don't know. That's why I'm asking you.
The only way that we know how much of one thing reacts or gives another thing is the coefficient. But the coefficients are moles, not grams. And so in order to use the conversion factor given to us by the coefficients, we have to convert from the grams that were given into moles. Then we can use the coefficient to go from moles to moles. And then we have to take the moles that we calculated to calculate the grams that we actually wanted in the end.
That
So
would
is
be
it-
the 2 moles of sodium in the top, right?
So it's moles of NaCl.
Moles
Moles of
of sodium.
sodium, and that would be the 2, right? It's up there?
At this point, we're just converting grams to moles. So this is just like we did the first step down here. We converted grams to moles. So 1 mole of sodium weighs how much? 23. Now we convert our grams to our moles. What unit goes down here? You just take that, stick it down here.
So then we'll look for it.
Now we can go from moles of sodium to moles of chlorine. So now what number goes here? 1. The coefficient on Cl2 is 1, and sodium is 2. That's my unit down here. Moles of chlorine. And what goes up here? Grams of chlorine. You can convert moles of chlorine to grams of chlorine. What number goes down here? 1 mole of chlorine weighs how much?
70 point something.
71.
71 for the
Each chlorine is basically 35.5, and there are 2 of them, so that comes out to be 71. .2. So, question?
No.
So do you see the different steps that are in here? Right in the middle, we have our moles to mole. From here to here was our grams to moles. From here to here was moles to grams. If you put all the steps together, you can go from grams to grams. And so the longest possible stoichiometry problem is grams to grams. Anything other than that is just a portion of it. And so if you can do this, you can do all stoichiometry problems.
Oh, so these other numbers we were working with, we got them at the periodic table?
That one and that one. Yes.
And that will be called what, the mole on the periodic
The
table?
molar mass. The molar mass of sodium is 23. The molar mass of chlorine is 35.5, but there are 2 of them. And so times 2 is 71. This problem looks a little bit different. What's different about this one than the last one?
Telling you.
You want to know what's going to be produced?
You want to know which one's produced? What about the numbers that they give you? They give you 2 of them. And so it says, what mass of sodium chloride will be produced when 9.2 grams of sodium reacts with 14.2 grams of chlorine? You can't plug in 2 numbers in the top left corner. And so what we call this is a limiting reactant problem. We have 2 reactants. In this case, we know how much of each we have. They're going to react with each other, and as they react with each other, they're going to make sodium chloride. Eventually, as they're reacting, the amount that you have left is going down. One of them is going to run out. one of them is going to run out, and one of them is going to have some left over. So when one of them runs out, your reaction stops. Does that make sense? You can understand that, right? If you have two ingredients and you run out of one, your reaction is going to stop. That is called your limiting reactant. How much of that reactant limits how much product you can make. So in this case, in order to figure out how much sodium chloride you're going to make here, you have to do two stoichiometry problems. You have to do one with the sodium to figure out how much sodium chloride you make. Then you have to do another one with your chlorine to figure out how much sodium chloride you make. Whichever one gives you the least amount of product, that's the amount of product you're going to get. So here, we're going to do the 9.2. Is that what I just erased?
No. So for each one, you're trying to get to NaCl,
Correct.
grams of NaCl.
And so we said if we start with 9.2 grams of sodium, how much sodium chloride do we make? In this case, we completely ignore the chlorine. It's like a completely separate problem. So we went grams of sodium, converted it to moles of sodium, used the coefficients to go from moles of sodium to moles of sodium chloride, and then went from moles of sodium chloride to grams of sodium chloride. And that says we get 23.4 grams of sodium chloride. So that's half of the problem. Now we have to do the second half. Where do I start in the second half?
14.
The 14.2 grams of chlorine. That's my unit down here. Grams of chlorine. That's my unit up here. Moles of chlorine. What number goes here? 1. Down here? 71. What unit goes here? Moles of chlorine. Copy it down. Now where do you want to go up here? Moles of NaCl. What number goes up here? 2. And down here? 1. Unit down here? Moles of NaCl. And up here? Grams of NaCl. And 1 mole of NaCl weighs 58.44. And it comes out to be 23.4 grams of NaCl. So in this case, was one of them limiting? No. In this case, you had exactly the right amount to completely react with each other. And so how much sodium chloride are you going to make? 23.4 grams. Because the question asks, what mass of sodium chloride should be produced when you react those two things together? 23.4 grams.
So say you get one that's smaller, then the answer to the question would be the one that's bigger?
Smaller.
Oh, smaller. Oh, yeah, because
Yeah.
bigger ones out.
We'll have an example. So but this is telling you, did we talk about conservation of mass? Okay. The law of conservation of mass means if you have a beaker and you put 9.2 grams of sodium in and 14.2 grams of chlorine in, you don't lose or gain mass. The mass that you put in is the mass that you get out. And so, if the only thing you get out is sodium chloride, the mass of sodium chloride has to be those two added together.
So we didn't have to do all that?
We did, because we didn't know that they came out equal. It's what this is a way of sort of testing yourself.
So, but that's always correct, if you add them both together, that's how much you're gonna get?
Only if they are perfectly balanced, which they won't be. That's that reaction happening. So 9.2 grams of that, 14.2 grams of that gives us 23.4 grams of that.
Were we doing the same thing over here? I know
Same.
she just asked that, but
Same thing as what?
we got the same answer over there, so I'm wondering what the second part, what were we trying to look for?
So the question says we're reacting 9.2 grams of sodium with 14.2 grams of chlorine. Just knowing that, we don't know that they are equal to each other. We have to do one stoichiometry problem to figure out how much product we can make with the sodium that we have. We have to do a second problem to figure out how much product we can make with the amount of chlorine that we have. And it just so happened that they both came out to be exactly the same. And so because you don't know they're the same until you do the math, you have to do the math. So I'm sure in this case, they will not come out to be equal. So this is a space shuttle liftoff, and it says 1.8 times 10 to the 8 grams of hydrogen is burned. How much is 1.8 times 10 to the 8? A lot. Times 10 to the 9th is a billion. So that's 180 million grams of hydrogen. The question says, first question says, what is the mass of oxygen consumed? Mass of oxygen consumed. So, in our stoichiometry problem, this is a grams to grams again. You've got 1.8 times 10 to the 8 grams of hydrogen. What's the molar mass of hydrogen? Be careful.
Oh, yeah.
2. It's H2, and so I'm just going to call it 2. One mole of hydrogen. We're trying to get to oxygen. So what's my unit up here? Moles of oxygen. Oxygen is 1. Hydrogen is 2. Moles of oxygen. What goes up here? Grams of oxygen. 1 mole weighs 32. And what do you get?
Is oxygen always 32?
If it's O2, it's 32. Each oxygen is 16. There are 2 of them in O2.
Oh, if it's O2.
If it's O2. So 1.4. So we react 1.4 times 10 to the 9th, that's 1.4 billion grams of oxygen to lift off a space shuttle. Second part of the question was, what mass of water vapor is produced? When you burn hydrogen, you make water. So if you're burning all of this oxygen and all of that, with all that hydrogen, how much water do you get? grams of hydrogen and moles of hydrogen, just like we did. But we're going to water instead of oxygen. And then convert your moles of water to grams of water. And it comes out to be 1.6 billion grams of water. So imagine, picture a space shuttle taking off. We're in Florida, you've probably all seen it. What's behind the space shuttle as it goes up? A cloud. What's a cloud made of? Water. That's what that is. It's the water coming from the space shuttle, from the reaction of the hydrogen with the water, with hydrogen with the oxygen in the air to make the water. So in this case, because we're, yes? So in this case, because we have hydrogen in the space shuttle that we're burning, is burning with oxygen in the air, it's assumed that we have more than enough oxygen to burn. Okay? There's all the oxygen in the world, literally, that you can burn. And so, hopefully, there's enough oxygen in the atmosphere to burn that much hydrogen, which there is. And so we say that oxygen is in excess. There is an excess amount of it. We have more of it than we need. And so the reaction of that space shuttle stops when the hydrogen runs out. The hydrogen, in that case, is our limiting reactant. Got it? Thank you. So here's another example of a limiting reactant. Okay? What this is hydrochloric acid in a beaker that we drop some magnesium into. Okay? When you drop it in, it sinks to the bottom and it starts bubbling. Okay? It's making hydrogen gas. We'll do this in the lab. After a while, that is what's left, and it's no longer bubbling. Just looking at this picture B, which do you think is the limiting reactant, the magnesium or the hydrochloric acid? Got magnesium, any hydrochloric acids? One tentative one. He's right. It's the hydrochloric acid. The way you can tell by looking is the magnesium gone? No. The magnesium is not gone, which means it didn't run out. Which means the magnesium must be in excess. If magnesium is in excess, the hydrochloric acid must have run out. Hydrochloric acid is clear. It looks like water. So you can't tell by looking at it the hydrochloric acid is gone. But the reaction stopped, so something ran out. And it definitely was not the magnesium. So the hydrochloric acid must have run out, which means it is the limiting reactant. If you start again, and then after a while you have that, what is your limiting reactant? Magnesium. The magnesium is your limiting reactant. It's gone. If it's gone, it limited the amount of product that you could make. It limited how much reaction could happen. So in this case, magnesium is your limiting reactant. So if you're just looking at it, you can tell pretty easily which one's your limiting reactant. But in this case before, we had these two problems. You couldn't just look at the number of grams and figure out which one was limiting. You had to do the math. The limiting reactant is the thing that runs out. And when it runs out, the reaction stops, so it determines how much product you can make. And so, if you have a problem like we have this much of this reactant and this much of the other reactant, you have to do both. And the one that gives you the smallest amount of product is the one that must run out first. And so that is the limiting reactant, and however much product it gives you is the amount of product that you will get. Here's another visual picture. This is an iron nail in a solution of copper chloride. Which would you say is the limiting reactant here? Yeah. Copper chloride. Why do you say that? The blue is gone, and the nail is still there. So because the nail is still there, it must not be the limiting reactant. So even if this was a clear solution, we could tell. But because it's blue, it's even more obvious. Blue is gone. You can think of these as making something other than chemicals. You do this all the time. Imagine you're making this solar car. And to make a solar car, you need a frame, a solar cell, a motor, and a set of 4 wheels. If you need to make one of these, and you have one of each of these, but you don't have any wheels, your wheels are your limiting reactant. You can't make a solar car without wheels. So if you have these number of parts, how many solar cars can you make?
3.
Why 3? You only have 3 sets of wheels. You have 4 bodies, 5 solar panels, 6 motors, but only 3 sets of wheels. So assuming you had to put 4 wheels on a solar car, and you weren't thrifty and made a tricycle or something, you can only make 3 solar cars. Here's another way of looking at it. It's still visual, but it's a reaction. This is a reaction of hydrogen with oxygen to make water. If you have this, you have these things available to react, which is the limiting reactant? How do you know? So she looked at the reaction, she looked at the coefficients, right? It told you you need 2 of these for every 1 of these. And so yes, there are more hydrogens here than oxygens, but that in itself does not mean that hydrogen is in excess, because you need 2 of these for every 1 of those. And so if you put those 2 with that one, those 2 with that one, those 2 with that one, still got these 2 left over. So hydrogen is in excess, oxygen is the limiting reactant. How many waters can you make? 3? 6. You get 2 waters for every 1 O2 that you have. We have 3 of the O2s, so we get 6 waters. Another way to look at it is every water has 1 oxygen atom. And we have 1, 2, 3, 4, 5, 6 oxygen atoms. And so we'll get 6 waters. Let's take our break here. How many slides are left? 12? Let's take a longer than normal break. We'll start at 7:30. So about 15 minutes.
So he will be that drop down.
No, it's okay. I was going to say, oh, you do that too.
I thought don't worry.
I see a lot of people doing that. No judgment
No,
here.
Why would you even say that?
No, I don't picture that. I don't think there's nothing else.
Oh, yeah, let me see this sandwich I have. Is that yours?
Yeah.
whole thing in. I only put the reaction.
Was it the last problem?
Yeah.
Everybody got full credit. Don't worry about it.
Oh, okay, so
It
that's
was
already,
a mess.
oh, okay, cool. And then, I was wondering if there's like any other extra credit opportunities, like,
There will be an extra credit question on each exam. And then there will be an extra credit assignment that I haven't given it up yet.
oh, okay, cause, I figured it out with the inbox thing. I assumed it would like light up under like where you see your different courses, but it's like very obscure and kind of vague in the sidebar, so I didn't know about it. And then I have an 80 some, well, I have a 79.9 at this point, and I'm just really worried about, I work a lot, so I don't really have the time to study, and that's the extra credit. I wanted to ask about that, and then,
The extra credit will be, I haven't signed it yet, but it will be up to 3% of the grade. 30 points. There will be a lot of work that goes into getting it. So you have to work for it. I think with a decent amount of work, you should be able to do it.
okay. Because I mean, this is definitely, I'm not very good with science or math, so this is very hard for me, and I just want to know there's hope if there is extra credit, maybe.
What
kind of
grade? You see it in the- yes.
I'm hoping I can at least get C.
So after today, the class is going to change a lot. We're going to get away from reaction. We're going to get into more of a simple algebra.
Okay, I'm.
For some people that's good, for some people that's bad.
Mm-hmm.
So you can make your own decision whether you think it's good or bad.
Like this with the code. This whole thing is confusing to me because of the boxes.
From here on out, there's going to be a lot of solve for X.
Oh, okay.
In my experience, that's easier for students as long as they don't slack off towards the end of the semester. It's like the material is easier because they don't try as hard, and so their grade stays the same.
Oh, okay. Got it. Okay. So there's some. Okay. Sweet. So now I need to know.
I would say, that's what you have in the moment. I would say it's definitely low.
Okay. Cool. I'm trying to really, like take all like my weekends to like study up and learn, but
The best suggestion I can give is if you don't understand one of the Canvas homework problems, ask me.
Okay. I'm usually pretty good with those. It's like when I'm just put on the spot and I have to,
Okay.
then I'm like, I trust drop I
It's
need
the-
like examples.
I really, but even if Wiley worked like it's supposed to, the Wiley questions would be harder. But it's the Canvas questions that are really what tell you if you know what you need to know to put it in.
Okay. Yeah.
So if you just focus your time, which we all do, focus on you have to do the Wiley ones. But when
Yeah.
you're studying, focus on the Canvas ones. And then go to your, if you don't understand it, you may have to go back to your notes for something that's not directly asked,
Right.
but you have to understand in order to get it.
Oh,
You know what I
okay.
mean?
Yeah, there's a lot of factors.
Yeah,
Things.
because things kind of build on each other.
Right.
Even though there isn't a question specifically asking you about one thing, you may have to study it in order to get the question that you want.
Okay. Cool. Cool. Thank you.
Anybody write with black pen and know they scribbled the top of their paper?
It was probably.
Oh, that, I think that's me, yeah. Sorry.
Did you get it right or wrong?
I wrote B.
Okay.
I agree.
Oh, you're better. I finished it at 5:55. At 5:55 I was sent. I was like sent. Seriously. Of course. No, but that's for like not everything though. Oh my goodness, this shops are giving me up forever. We are not late.
Silver is on the silver dog. So I just forget him. Yes. Oh, you mean like them over there? The skills thing? You have to go. You never show up.
No, I'm like, how's it only 7:30?
How can you really get conversation wrong when it says, why do you think? I mean,
So he did, that's an opinion question. He wasn't. I'm gonna go with you on this one. I'm sorry.
You're bringing it.
Oh, wait, so we get that grade forgiven too, man?
No. No, I think you need to hold yourself to better standards than that.
Well, I put that adding heat makes the reaction faster, like it's a, oh gosh.
Wait,
what
because that's
yeah. Thank you.
No, he changed it,
that sounded
What is wrong?
like what
I said 100.
No,
Working with somebody.
Yeah.
So it's not a felony?
What? No, that's exactly what I wrote.
What?
What happened?
My answer should be right.
He just had
I said, he said adding
Who are you comparing it to?
Myself, you wrote in what you wrote.
How do you prove
You
it?
wrote heat excites
I'm
electrons, and we
sorry.
wrote adding heat to an element changes the reaction and makes it faster. I guess that
But
doesn't.
that's not a reaction.
You're right.
What do you put?
You're right.
You can't even tell. How can you bet that?
question.
No, you didn't.
Not
They did not, that last one was right. There's no way.
Wait, what did you do? How do something you can test? How can you test that bird? Or
Open it, open.
Or flies
What
because
he
it has
likes.
Open it.
flies because it has to.
Just
Open it up.
That's just as good. Open it up.
No, I have nothing to do with that.
Yeah, they go to the TLC to apply for to be a
Left it
tutor.
blank.
But they were only here for summer A.
He was never here.
Right, he's officially gone to summer B then.
I mean, we just struggled to get him. So we were wondering, so is there any way we can get a tutor?
There's a tutoring in the HA building. I don't know if they are here at summer B. That's provided by the college,
Okay.
not the department. So I have nothing.
Right now, we have nobody for chemistry tutoring at all.
I think.
What?
So it's all
Look
in my
into,
lessons?
send me something on point art. I know that the tutoring here is done. Assuming we're in summer B, are we in summer B yet?
I think so, because there's like no cars here.
Oh, that's not
They told me before the semester started there would be nothing.
I wish I
in
would have pressed some back.
So like when you stop, you just stop.
I did not know I did that.
If you're stuck, you're not stuck. You need to email.
I know that's stuff.
Times in like, maybe it's
No.
still ended.
I figured it out.
Or like it will keep
Jane?
it happens.
You said I did.
Okay, so we're gonna pick up where we left off. So there are two ways to do a limiting reactant problem. They're both listed here, but I am only going to show you this last one, which is what we did up here. And that is my suggestion of how you should do it. Okay? I'm not even going to show you the first way, because for most of you, it would just be more complicated than it needs to be. And in a lot of cases, it doesn't solve any, it doesn't make any less work. It actually makes more work in the end. Okay? So the first way to do it, and if this makes sense to you and you want to teach yourself how to do it, that's fine, allows you to, if you have X amount of reactant A, Y amount of reactant B, say if I have this much of A, how much of B do I need? If I need 50 grams of B and I have 100 grams, I have excess B. If I need 50 and I only have 20, B is my limiting reactant. Okay? That's how that works. But you have to think about it. When you get to the end, it's not obvious, because it says you need this much. How much do you have? And is that enough? Is that not enough? And then which one is limiting? There's a lot of thinking involved there. The other way is exactly what we did. Do the math that you know how to do. Get two numbers. Whichever one gives you the least amount of product is your limiting reactant. And that amount of product is the amount of product that you make. Okay? Pretty much every problem that you come across here on a quiz or an exam is going to be two parts. Part A is which is the limiting reactant. Part B is how much product you can make. And so if you do it this way, with both parts, you already calculated how much product you can make. You just copy it from part A down to part B, and you're done. With the other way, you then have to go back and do another problem in part B. Okay? So my suggestion is to do it the long way in part A. That'll just make B easier. So here's an example. We are reacting phosphorus with oxygen to give us P2O5. The question says if we mix 0.5 moles of P4 and 5 moles of oxygen, which is the limiting reactant? Now the question doesn't anywhere here ask us how much oxygen we're going to make. or sorry, how much P2O5 we're going to make. So we don't have to calculate the P2O5 in grams. We can just calculate it in moles. Whichever one gives us the least number of moles will be our limiting reactant. So we can just do a moles to moles conversion for P4 and a moles to mole conversion for O2, and then we're done. So I'm going to do the P4. I've got 0.50 moles of P4. I'm trying to get to moles of P2O5. I'm just going to do a one-step moles to moles conversion. What unit goes here? Moles of P4. And what goes up top? Moles of P2O5. What number goes here? P2O5 is 2. And what number goes down here? 1. And so 0.5 times 2 equals 1.0 moles P2O5. Then we do the same thing down here with our oxygen. 5.0 moles of oxygen. Moles of oxygen. Moles of P2O5. Oxygen is 5. P2O5 is 2. 5 times 2 is 10, divided by 5, 2 moles P2O5. So, which reactant is our limiting reactant? P4. So what people like to do on a problem, and I tend to give them benefit of the doubt, but you don't always want to shoot for the benefit of the doubt, is they'll do this. And then they'll circle that and say, limiting reactant. That's not the limiting reactant. That is the limiting reactant, and you know that based off of that number. Okay? So P4 is your limiting reactant because that one gave you 1, that one gave you 2. So this came from the limiting reactant, which means P4 is your limiting reactant. So if the question had a part B and said, how much P2O5 can you make? What's your answer?
Do you have to change it to grams? No?
If the problem doesn't say, give it to me in grams, you can give it to me in anything you want. So I would give it in moles. 1.0 moles P2O5. Just copy that down from part A to part B. So we can do part B. 0.20 moles of P4. 4, 5 equals 0.40. 5. And then 1 mole of oxygen. Times 2 divided by 5, 0.2 P2O5, which is our limiting reactant. Oxygen. O2 is our limiting reactant. How much P2O5 can we make? 0.2 moles. And then the last one, we've got 0.25 moles P4 and 0.75 moles of oxygen. Five times 2. 5. And we've got 0.75. 0.75 times 2 is 1.5. It's 1.5 divided by 5.
I'm thinking 0.5.
1.5 divided by 5. What's my limiting reactant? Ah. Okay.
Put up 2 instead of 5.
Where?
Moles. Just 5 1.
Here?
Yeah. Oh, you put 2 moles of PT05 instead of 5 moles of Oh, this on the board is wrong.
Yeah.
I'm sorry.
2 moles. P4. 1 mole of P4. 2 moles.
They're putting oxygen and you're putting P2O5 in place of where you're putting that. They put oxygen.
Oh. This says there's no limiting reactant. And so if there's no limiting reactant, these should come out equal. 1 mole of O2, 5, 1 times 2. Oh. I did the math in my head and I did it wrong. 1 times 2 is 2. 2/5, 0.4, not 0.4.
That one there.
So now there is no limiting reactant. Sorry for that. This is more like what you would see on a quiz. So there's part A, identify the limiting reactant, and then part B, how many moles of ammonia can you make?
Don't erase that. Thank you.
So we're going to do 1A, 2 moles of nitrogen, 5 moles of hydrogen. And I would save yourself some trouble and look ahead to part 2. It says how many moles of ammonia can be produced, which means up here, we again just have to go to moles. If this asks you how many grams of ammonia can be produced, then you might as well go to grams up top. So we will just go to moles again. So we've got 2 moles of nitrogen. What is the limiting reactant? Hydrogen. This number is smaller than that number, which means hydrogen is our limiting reactant. How many moles of NH3 can be produced? 3.3 moles. It's a smaller number. Somebody want to come up and do part B? 3.1 moles of nitrogen. Can't say I did not.
No.
3.10 moles of N2. 1 mole of N2. 3.1 times 2 is 6.2. .4 divided by 3. .4 divided by 3. 6.1. 8. 3 6 8. Is it 8 0? What's the limiting reactant? Nitrogen. This number is smaller than that one. So nitrogen was the limiting reactant. And how many moles of NH3 can be made? 6.20. If this question said how many grams of NH3 can be produced, my suggestion would be in both cases, just add the extra step under the N to go from moles to grams.
So you would do like how many grams of NH3 over 1 mole?
Right. 1 mole equals 17 grams of NH3. 14. Nitrogen is 14. 15, 16, 17. Yeah. So you like this one, it says what is the maximum amount of aluminum chloride in grams that can be produced?
Not only like that side. I'm too slow, so it takes me a while.
You can copy it.
Hmm?
You can copy it. I don't have it.
Thank you.
So, anybody want to do this one? No, I don't want to see a professor evaluation saying he just gets on the board and writes and doesn't do anything, okay?
I don't even, are you on for, blah, 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 blah. Right by professor?
Yeah.
Are you?
I also don't want to get it sent to my boss saying,
Like it's sent to your boss?
no, the official Santa Fe one.
Oh,
Because I am on video right now offering. You know, 0.40 grams of aluminum. This one we're starting with grams, and we have to go to grams. So actually, let me start further left. Grams of aluminum. Aluminum, 27. 27 grams of aluminum. 1 mole of aluminum. What's my unit up here? Where am I trying to get to? In the end.
Grams of aluminum? No?
Grams of aluminum chloride in the end. And so I have to go to moles of aluminum chloride first. 1 mole of aluminum of, can't do that. 27 plus 35.5 times. No, they did it the other way. 130.3? Thank you. Definitely can't do that. aluminum is
27 plus 35 plus 5.
27 plus 35.3 times 3.
Oh.
So 3 of the chlorines, 1 of the aluminum. What does that come out to be?
Yeah, 1.97.
1.97 grams of AlCl. Now we're going to do the same thing with our 0.6 grams of chlorine.
You said the sig figs for any of these are going to be, what's it dependent on?
What is that? What's my unit here? I've gone from grams of chlorine to moles of chlorine. Moles of chlorine to what? Moles of AlCl3. The last step here is exactly accurate. It sounded like, it's a very soft knot. Maybe there'll be something on the video, like somebody's. CO2 is 3, AlCl3 is 2.
Is somebody?
It might have been a pressure thing. Someone opened another door.
There's a person there.
He went in the room
It's
across the
custodian.
hall. Yeah.
Did he knock on the
He
door?
came in the back and then he's been walking around.
I get 0.75. I need at least one person to confirm it. Yeah. Thank you.
I second the motion.
What is my limiting reactant? Chlorine. What is the maximum amount of aluminum chloride in grams that can be produced? 0.75 grams of aluminum chloride. I didn't do sig figs up here because that number is not my answer for that. And so I didn't bother doing the sig figs yet. If I had picked this one and I copied it down to here, I would need to then look at the sig figs on it.
So you're not going to be looking at our work.
Sig figs in your work do not matter.
Okay.
Sig figs only matter on your answer.
What is that? Is that 71?
There?
Mhm.
Yes.
And 27 at the top.
27.
I have a question, like for some of the masses you rounded, so.
I tend to round them if they're very, very close. And so for chlorine, it's very, very close to 35.5. And so I round it to 35.5, and then 2 of them is 71. Oxygen is actually exactly 16. Nitrogen, 14.01. I just call it 14.
Okay, so hydrogen.
I would just call it 1. Something like strontium, I would put in the whole thing. It's just things like hydrogen, oxygen, nitrogen, and carbon, they're very, very close to a number, and you use them so often that you just get them memorized. And so I know oxygen is 16, and so O2 must be 36. I don't even have to look at it. but if I had to look up carbon is 12.01 every time, add a lot of time to what I would do. Okay, is this the last? I think this is the last idea that we've talked about. It's percent yield. These problems tend to have a part C to them as well. It says, if you do this reaction in the lab and you actually get this much product, what is your percent yield? And calculating the percent yield is very easy. You're going to take your actual yield divided by your theoretical yield. So your actual yield is what you get in the lab. This is a number that will be given to you in the problem.
This is pretty much the percentage of error that we did before.
Yes. And so what we did before was the actual, you calculated the density, and then I gave you the actual density. And so it's the same thing. Yes. It's what you measure divided by what the right answer was. So in this case, the actual yield will be given to you in the problem. It will say, if you run this in the lab and you get 5 grams of product, what is your percent yield? This, whatever you copied from here, the part B, is being your amount of product that you made, is your theoretical yield. This is what you should get on paper. If everything works perfectly, that's how much product you would get. But when you run a reaction in the lab, you do not get 100%. Okay? It just does not happen. Most of the time, you end up with less than 100%. Because if you pour something from one container into another, a little bit gets left behind. And reactions normally don't actually go to completion. We'll learn why in a couple weeks. But reactions don't actually, a lot of times, go to completion where one of them runs out. It'll actually stop before the reactions run out. So you don't get how much you should. And so you're going to take the actual divided by the theoretical times 100. So if you're supposed to get 100 grams and you get 30 grams, what's your percent yield? 30%. You're supposed to get 100, you got 30. 30 divided by 100 times 100 is 30%. Yeah.
So you said that the given calculations are actually?
Is your theoretical. So theoretical is always on paper. And we did this on paper, we calculated what we're supposed to get. This is our theoretical. And your actual is what they will give you in the problem. And this test taking strategies. This is part C. If you mess up part A, you're obviously going to mess up part B. If you mess up part B, you can't possibly get the right answer for C. I will grade C completely independent. So I will make the assumption that the number you gave me in part B was correct. And then if you did the calculation here correct, you'll get full credit on C. So if you actually got 30, and the problem tells you that, and you were supposed to have calculated that the theoretical was 100, but you calculated it to be 50, you did something wrong. If you tell me 30 divided by 50 equals 60%, you're going to get full credit for C. Okay? You don't have to get A and B correct to get C correct. If you, for some reason, don't know what number that is and what number that is, just write the equation for me. You'll get something. Okay? If you just write that, you'll get something out of it. Is this the last slide?
Secondary one.
We'll just do this one. So we'll skip the slide for it. So this is more of a real life situation of what you could do in lab. And so when I took chemistry in high school, we made aspirin. And no, I didn't go to some rich kid high school. Making aspirin's really easy. And so you're making aspirin, and it says using the amount of limiting reactant, she calculated the amount of aspirin she should form. It says she already did all of this math. And she calculated she should form 8.95 grams. She makes her aspirin in the lab, she measures it, and she has 7.44 grams. What is the actual yield of the aspirin? Which one's the actual? 7.44. What you actually made in the lab. So the actual is 7.44. And the theoretical yield is what? 8.95. And so, how do you calculate the percent yield? 7.44, the actual, divided by the theoretical 8.95. What is it? 83.0%. 83.1%. Okay? So, the type of problem that you would run into is kind of like this. You have to do 2 steps, pick the smaller amount of product, copy it down to part B. That's how much product you can make. And then take your actual that will be given to you, divided by your answer in part B, how much you calculated you should make, times 100, 83.1%. Does that make sense? Can you picture what this problem was going to look like? It's going to be on the exam next week. And I'm guessing it's probably also on the written problem on the Canada's homework this week. I don't know that for certain. Questions about this?